MSA for Continuous Data and Gage R&R Test. What is MSA for Continuous Data? Let's talk about MSA, or Measurement System Analysis, for continuous data. MSA helps us evaluate whether our measurement system is capable of doing three key things. First, it must be able to accurately measure continuous variables. These include things like time, length, weight, or pressure, anything that can take on a wide range of values on a continuous scale. Second, it should be able to detect process variation, meaning it should help us see when a process changes or shifts. And finally, it must do all this without introducing too much measurement error. A good measurement system gives us reliable data that reflects the actual process, not noise or mistakes from the tools or methods we use. Now, remember that continuous data means values that fall on a scale with infinite possible values within a range. They're not limited to fixed steps. Here are a few real-world examples of continuous data. The diameter of a bolt measured in millimeters, delivery time recorded in minutes, or temperature in degrees Celsius. Why MSA for continuous data? Now, let's understand why we even need to do MSA for continuous data. The first thing to remember is this: every measurement system adds some error or variation. No tool is perfect, whether it's a stopwatch, a thermometer, or a caliper. So, our main goal with MSA is to separate the two types of variation. How much of the variation is actually coming from the process itself, and how much is coming from the measurement system? That is, the tools, methods, or even the person taking the measurement. This is critical because if your measurement system is unreliable, if it's adding too much error, then the data you're using for analysis might not reflect the real process at all. Here's the key message I want you to take away. Never assume your measurement tool is perfect. Prove it. Because if you don't, and your system adds too much variation, you risk making the wrong decisions based on flawed data. Let's talk about measurement variation, which is a critical concept in quality management and process control. Measurement variation refers to the variability that arises from the measurement process itself, rather than the actual process being measured. It's important to understand that even a stable process can appear unstable if the measurement system is not reliable. There are two primary sources of variation in a continuous measurement system. 1. Repeatability. This is the variation when the same operator uses the same equipment to measure the same part multiple times. In other words, it's the consistency of results under identical conditions. 2. Reproducibility. This type of variation occurs when different operators use different equipment, but measure the same part. It reflects the impact of changes in people and tools on the measurement. Together, these two components form the total measurement variation, expressed in the formula. Total measurement variation equals repeatability plus reproducibility. Our goal is to minimize both repeatability and reproducibility errors. A good measurement system should show minimal variation regardless of who measures, with what, or when. Understanding and reducing measurement variation is essential for reliable data and effective decision-making in any quality improvement project. In this section, we focus on measurement system analysis, or MSA, specifically for continuous data. These are measurements that can take on any value within a range, such as length, weight, or temperature. When we evaluate the effectiveness of a measurement system for continuous data, there are two primary tools we rely on. 1. Gauge repeatability and reproducibility, often referred to as Gage R&R. This tool helps us understand how much of the observed measurement variation is due to the measurement system itself. It includes repeatability, variation when the same person measures the same item with the same equipment. Reproducibility. Variation when different people use the same equipment to measure the same item. Second test retest, repeatability study. This is a simpler study that looks only at repeatability. It involves a single operator measuring the same part multiple times under consistent conditions to evaluate the consistency of the results. These tools are fundamental in validating whether our measurement system is reliable enough to support process improvement initiatives. Let's now take a closer look at both tools to understand how and when to use them. Now let's walk through the key steps involved in conducting a gauge repeatability and reproducibility Gage R&R study. The first step is to select 10 to 30 parts that represent the full range of variation we typically see in the process. This ensures the study covers all possible scenarios the measurement system may encounter. Next, choose 2 to 3 operators, also called appraisers. These should be people who typically perform the measurements during regular operations. Each operator will then measure each part 2 to 3 times. This allows us to observe consistency within an operator, repeatability, as well as differences between operators, reproducibility. It is crucial to randomize the measurement order. This prevents any bias due to sequence effects or operator fatigue, and simulates real-world variability more effectively. Finally, make sure to record all measurements in a matrix format. This structured data set will be used to analyze and quantify the repeatability and reproducibility components of variation. Following these steps correctly ensures a valid and reliable Gage R&R study, helping us assess the adequacy of our measurement system. Let's now look at a practical example of how a Gage R&R study is conducted in a manufacturing setting for continuous data. Step 1. We start by selecting 10 metal rods, each with different diameters. This allows us to capture a representative range of variation in the parts being measured. Step 2. Then we have 3 inspectors, or appraisers, who will measure the diameter of these rods using the same caliper. It's important that the same measurement instrument is used to ensure consistency across readings. Step 3. Each inspector will measure each rod twice. This repetition is key to assessing the repeatability of the measurements within each operator, and also helps evaluate the consistency across operators. At the bottom of the slide, you can see an example of how the data might look. Each part is measured twice by all 3 operators, and the results are recorded in a table format. For example, for Part 1, Operator 1 recorded 15.21 and 15.20, Operator 2 got 15.21 and 15.20, and Operator 3 recorded 15.22 and 15.24. This data matrix is then analyzed statistically to determine how much of the variation is due to the measurement system versus the actual parts. This example helps us visualize how the Gage R&R study is structured and why it's crucial in evaluating the reliability of our measurement process. Now let's look at a Gage R&R example from a service environment, which is just as important as in manufacturing. In this case, the project focuses on reducing customer onboarding time, a critical metric in service delivery and customer satisfaction. To assess the reliability of the measurement system, 3 staff members are assigned to measure the onboarding duration for the same 10 customer cases. Each case involves reviewing the same set of files, so the input is consistent. The key question here is, are the measurements consistent across staff and repetitions? Each staff member measures the duration twice, and then we compare the timing results. If we find that there's a lot of variation, either between staff members or between their repeated measurements, it may indicate issues with the measurement method, instructions, or even understanding of the process. This kind of Gage R&R study helps us identify and eliminate variation in the measurement system before we move on to improve the process itself. It ensures that any improvements we make are based on reliable and consistent data. Let's now understand how to interpret the results of a Gage R&R study. When we run a Gage R&R analysis using software like Minitab, we get three key outputs. 1. Percent Gage R&R. This tells us the percentage of total variation that comes from the measurement system itself. 2% repeatability. Variation when the same person measures the same part multiple times. 3-point reproducibility. Variation when different people measure the same part. We use these results to evaluate how reliable our measurement system is. In the table on this slide, you can see the interpretation of percent Gage R&R. If it's less than 10%, that's excellent. The measurement system adds very little variation. Between 10% and 30% is generally acceptable, but it depends on the level of risk and how critical the measurement is. Anything above 30% is considered unacceptable. It means the measurement system contributes too much variation and needs improvement. So, a lower percent Gage R&R means a better measurement system, one that allows us to trust the data we're collecting for decision-making. Now let's talk about what leads to high measurement error in a process. Measurement errors can significantly affect the reliability of our data. This slide highlights some common causes of high measurement error. Poorly calibrated equipment. If our tools or instruments aren't properly calibrated, the measurements they provide won't be accurate. This is a technical issue, but a very frequent one. Inconsistent measurement methods. When the method used to take measurements is not standardized or varies between operators, we get inconsistent results. This is often due to lack of documentation or unclear procedures. Environmental factors. Conditions like lighting, noise, and temperature can interfere with measurements, especially in sensitive environments. These need to be controlled or standardized as much as possible. Lack of training. Even if we have the right tools and methods, untrained or poorly trained staff can introduce errors. Training ensures consistency in how measurements are taken. The takeaway here is that both human and technical factors contribute to measurement error. By addressing these root causes, we can significantly improve the reliability of our measurement system. This slide explains the concept of a test-retest or repeatability study, which is a key part of measurement system analysis. The focus here is solely on repeatability, meaning we are looking at how consistent one operator is when using the same equipment to measure the same part multiple times. For example, imagine Inspector A measuring the diameter of the same bolt 10 times in a row using the same instrument. The goal is to check how much those repeated measurements vary. If the measured values are very close to each other, we say the system has good repeatability. But if the measurements vary a lot, it indicates poor repeatability, which means there's inconsistency in how the operator or the equipment performs. This kind of study helps us understand how much variation is coming from the operator and equipment alone, without the influence of different parts or inspectors. Repeatability is a foundational check before we move on to more complex studies like reproducibility, which involves multiple operators. This slide answers an important question. When is it appropriate to use the test-retest method on its own, without a full Gage R&R study? There are three key scenarios. 1. No multiple operators available. Sometimes in small teams or during night shifts, we may not have more than one trained operator. In such cases, we can only assess repeatability, not reproducibility, so the test-retest method becomes the best practical option. 2. Tool calibration check. If we suspect that a measurement tool might be giving inconsistent results, We can use test-retest with the same operator measuring the same part repeatedly. If the variation is high, it might point to calibration issues. 3. Baseline study before full gauge R&R. Before jumping into a full-blown gauge R&R with multiple parts and operators, it's a good idea to do a quick repeatability check. This gives us a baseline understanding of how consistent the measurement system is under controlled conditions. So, while test-retest alone doesn't give the full picture, it's a useful technique when conditions or resources are limited, or when we just want a quick initial check. Now let's talk about some key do's and don'ts when conducting a measurement system analysis, or MSA, specifically for continuous data. Starting with the do's. Always use representative samples that cover the full range of process variation to ensure your results are valid. Randomize the measurement sequence to minimize any systematic bias. Make sure your measurement procedures are standardized across all operators to maintain consistency. It's critical to calibrate your equipment before the study to ensure accuracy. Train all operators beforehand to avoid inconsistencies in measurement technique. Use specialized software like Minitab or JMP to analyze your data correctly and effectively. If your Gage R&R results are poor, don't just accept them. Investigate the root causes. And finally, use a sufficient number of repetitions in your study to ensure the results are statistically reliable. Now the don'ts. Don't skip MSA just because you're using expensive equipment. Price doesn't guarantee accuracy. Don't allow operators to compare results during the study, as it can bias the outcomes. Don't ignore environmental factors such as lighting or vibration, as they can impact measurements. Don't assume your measurement system is good enough without supporting data. Always back it up with numbers. And don't use only one operator. You need multiple operators to assess reproducibility effectively. By following these guidelines, we can ensure the accuracy and reliability of our measurement systems, which is foundational for any quality improvement initiative. This slide highlights why measurement system analysis, or MSA, is so critical in Lean Six Sigma. First and foremost, data drives decisions, and in Lean Six Sigma, we rely heavily on data to make informed choices throughout our improvement projects. However, if the data we're basing our decisions on is flawed due to measurement error, then the quality of our decisions is compromised. Measurement errors can directly impact 1. Capability analysis. If your measurements are inconsistent or inaccurate, your capability indices like CP and CPK won't reflect the true performance of your process. 2. Control charts. These are only useful if the data plotted is reliable. Otherwise, you may see false alarms or miss actual issues. 3. Process improvement actions. If we misinterpret the data, we might address the wrong root cause or implement changes that don't actually help the process. There's a great quote on this slide. If measurement error is too high, you're chasing measurement error, not process variation. This means that without a proper MSA, you might think there's a problem in the process, when in reality, it's just the measurement system giving you faulty data. So, in essence, MSA is not just a checkbox. It's a foundational step to ensure the integrity of your data before you make any critical process decisions. This slide guides us on what to do when our measurement system analysis shows a poor result, specifically when the percent gauge R&R is greater than 30%. A gauge R&R value above 30% indicates that the measurement system is contributing significant variation, which is unacceptable. At this point, we should not proceed with data analysis until the measurement system is improved. Here are 5 key actions we can take. 1. Investigate the root cause. Look into potential issues with the equipment, the operators, or the measurement method itself. Try to pinpoint what's contributing to the high variation. 2. Retrain operators. Sometimes measurement error stems from inconsistent technique. Ensuring all operators are well trained and following the same procedures can reduce variation. 3. Recalibrate the equipment. Calibration drift can cause serious measurement errors. Always check if the measuring tools are properly calibrated. 4. Improve the measuring procedure. Standardizing the method and ensuring it's well documented can help minimize inconsistencies. 5. Replace the tool if needed. If the equipment itself is inherently flawed or outdated, replacement may be necessary for accurate measurements. Finally, if after taking these corrective actions the measurement system is acceptable, then we can confidently proceed to the analyze phase of the DMA cycle. Remember, don't rush ahead with faulty data. It will only lead to faulty conclusions. This slide presents a real-world example of how measurement system analysis, MSA, can directly impact quality improvement in an assembly line. In this project, the goal was to reduce rework in the assembly process, with a focus on bolt torque measurement, a critical-to-quality CTQ parameter. We had 3 operators measuring the torque on 10 bolts, and each bolt was measured twice by each operator. This setup allowed us to assess both repeatability and reproducibility. The first Gage R&R result was 35%, which is clearly unacceptable. This high variation meant we couldn't trust the measurement system to make data-driven decisions. Upon investigating, we found that the torque wrench had inconsistent calibration, which introduced variability in the readings. The team decided to replace the tool. After the replacement, we conducted a second Gage R&R study. This time, the result was 9%, which is acceptable and within industry standards. With a reliable measurement system in place, we were finally able to move forward with process improvement efforts confidently, knowing that our data was trustworthy. This example emphasizes the importance of checking measurement systems before diving into analysis. Otherwise, you may be trying to solve a problem that doesn't actually exist in the process. This slide summarizes the key points to remember about measurement system analysis, or MSA, especially in the context of an assembly line process. First, MSA helps us quantify the error in our measurement system. It tells us how much of the observed variation is due to the measurement process itself, whether that's from the equipment, the operator, or the method. You'll notice it's mentioned twice here to emphasize its importance. Both repeatability and reproducibility contribute to that error. Next, the test-retest method only assesses repeatability, which means it checks how consistent one operator is using the same tool repeatedly, but it doesn't account for variation between different operators or tools. When looking at Gage R&R values, a result of less than 10% is excellent. It means the measurement system contributes very little error, so the process data is reliable. On the other hand, if Gage R&R exceeds 30%, that's a red flag. The measurement system needs to be fixed before we proceed with process analysis. Otherwise, we risk making decisions based on inaccurate data. Ultimately, a trustworthy measurement system is the foundation of good quality improvement. Without it, we can't truly understand what's happening in the process.